the main idea here is that, well, I want to give you this impression or this idea how you should think about the data samples that you have inside your data set, and how you can interpret it as samples coming from a specific distribution, and how you can validate whether this is a good representative of the original distribution or not. One thing that I would like to indicate here is that in practice, when you leave here and you start working, most of the thing that you do is just dealing with the data. Like in all the projects in machine learning that you do, typically most of the time you're just cleaning data, making it like in the normal form that you can use it for training or whatever you want to do. And after that, like doing the training or nowadays many people do prompt engineering, things like that. That kind of things are they are going to get very trivial for you. So the key thing that is always new in any problem is usually data. And now, usually we talk about data preparation. So data preparation is the procedure that you get from the raw data that you have collected in the environment into a kind of data that is clean and useful for your purpose. And it does not necessarily simply mean that you get and put the data in the right mathematical format. I mean, obviously that is a part of it, but that is not too much that we can talk about. The key thing is that when you get a data, you need to make sure that this data is somehow a good representative of the problem you're trying to address, okay? And there are a bunch of different ways to do that. One thing is that, for example, we do data augmentation. This is the particular one which I want to just mention here because this is one of the ways you can somehow reduce overfitting in your model. This simply means that you're going to get a bunch of new data samples and then you add it. I mean, you create a bunch of new data samples, you add it inside your data set, but at the same time, you need to make sure that those samples are not making any issue in your problem. The other thing is data cleaning. So obviously, you can again understand that what does it mean? Like you might have a bunch of samples which are not supposed to be there, right? And again, how we can handle them, we need to have the idea what is the right representative of the data distribution. And once we get this idea, then we get the idea why, for instance, we need to just get rid of things like duplicates, nulls, or outliers. We're going to talk about that quickly. And then data transform, sometimes you have specific data and then you want to just use it for one specific purpose. This data can be, for instance, represented in the latent space. And in the latent space, when you represent it, it's going to be a better representative as compared to the raw data that you have. This thing we're not going to talk directly here about, but we're going to talk about it later on in the last chapter when we talk about autoencoders. You can do dimensionality reduction. Those of you who had 1513, you know about PCA. We're going to mention it briefly in the last chapter. And typically, like if you have a financial data with huge number of entries, you usually, what you do, you just compress it into lower dimension because you know that the information is not too much. So many of those information can be represented in lower dimension. Things like that, we can do it. So you're going to gradually learn them through this course and other courses. But all of things that you do are basically coming from this simple fact that you're looking at the data coming from one specific distribution, and what you have in hand are samples coming from that distribution. What you want these samples to be good population representative of the original distribution. This is what we want to talk about today. So yeah, let's start with the augmentation, the idea of augmentation first, just intuitive illustration what that means. So in the idea of augmentation, what we want to do, we have a bunch of data samples. And we know that they are not enough. I mean, data is never enough for the task that we are doing. What we want to do, we want to increase these samples, right? And say we have this particular data set which has cat and dog images. And what we want to do, we want to increase the number of samples inside this data set, right? And we are not able to go out and take new photos of cats and dogs. We only want to work with that data set because of some reason, right? Now, can we think about this augmenting or increasing the data set size? Well, let's write down things more concretely. Say I have B, one batch of data with B different samples. X's, here are pixel vectors, right? The pixels of the cat or dog image. V is the label, right? It's, for example, 0 if it's cat and 1 if it's dog, right? Now, say that I have this particular algorithm. So this algorithm or this transform or this function, whatever you want to call it, this A has this property that it's going to get one vector n-dimensional, and then it's going to transform it into another n-dimensional vector, okay? One transform. It could be a simple matrix being multiplied with that vector, right? So I have this particular A, and then I pass one of the samples, say x1 was the cat image, and I pass it through this A, I get x hat, right? So I got the cat image, I did some transform on it, and I got x hat. And then I again show x hat. I see, well, it looks like a cat. Maybe the cat has been rotated, maybe the cat has been just flipped, something happened to the cat, that's okay. But at the end of the day, it's still a cat, right? One other thing is that I cannot see this cat, this specific cat image, inside my data set that I have. So what can I do? I can simply say that, okay, this new x hat with label 0, which is the label of the cat, I add it to my data set, right? And I have a new sample inside my data set, one extra data sample where, well, more data, right? And this could improve, right? So this is the very basic idea of augmentation. Now, in this idea that I wrote here, the only thing that you need to figure out is what is the key thing that we need for this idea to work? Algorithm A, right? I need to know this A. I need to know how I can transform one cat image into another cat image, right? This is something that I need to know. And yep, so this is my new data set. I can expand it, and this is the basic idea of augmentation. For images, for instance, we know lots of transforms, right? So for instance, you get this cat image, and you can do whatever you want on it. You can just shift things. You can rotate it, squeeze it, crop it, do whatever you want. These guys, all of them here, they are all cat images, right? And they are not inside your data set, right? And now you can add them with the label cat to your data set, and then this is going to be still new data for your task, right? But one question, if I do this, right, and I am trying to understand, like, what is the pattern of the ear for a cat, do you think doing this simply is going to help me? Well, no, it's not going to help me because this cat has exactly, I mean, all of these cats have exactly the same pattern of ear as this one, right? So if my task is as simple as just classifying cat from dog, right, this might help, right? But if I have a more complicated task, you guess that this is probably not going to help, right? And that is correct. This is because all of these samples are basically same sample, right? So they are not really independent samples, right? When you can compute one sample as a function of other sample, then they are not independent, right? Okay. So, but this idea could generally work, right? And this is something that people, I mean, still many people do it, right? Like in Python, in PyTorch or in Pandas, you have still geometric transform package where you can use them to just geometrically change your images, and by that increase the number of samples you have in your data. So it's not going to do sophisticated work for you, but it's still going to improve the performance of your training. So the key thing, as I said, you need to know this A, which is the kind of transforming one cat image into another cat image. If you predefine A, for instance, you put it to be a rotation matrix, which just gets the cat image and rotate it, this is what we call it augmentation by engineering. So augmentation by engineering, it simply means that you predefine this transform A, right? You would say, okay, I do know this transform is not going to change the context inside the image, so I'm going to use it for all the samples I have, and I make sure that the new transform version is not inside my data set, so I'm going to add it to my data set, right? So you can do different form of engineering for images. As I said, there are geometric packages inside Python. You can directly do that. So things like, for example, rotating, flipping, stretching, zooming, cropping, all of them you can do it. There are also other things like you can play with kernel filters. You can get one image and blur it, right? Or you can increase the intensity, and then all of them are still cat images, right? If your neural network is learning the pattern of the cat, it's supposed to also classify it as a cat, right? So you can also do that. You can just play with the color transform. So if you have RGB image, you can, flip the channels. There are other approaches. For instance, you can remove pixels. You can do it like in a pattern form, like one line of pixels are gone, or maybe you can do it randomly inside your image. And as long as your neural network is really understanding the pattern of the image, it still should be able to classify it as a cat, right? Because the cat image itself is not getting completely lost, right? So you can still do that, and there are also some more sophisticated ways. For example, you get multiple cat images and you somehow combine them in a way that is still a cat image, right? But it looks a bit different, right? And this might be more efficient way, right? Typically nowadays, with all of the current state of the art, we don't really need to do anything further. But early days, people sometimes even train a neural network to do that transform for them. You can do it, yeah. Always, if you want to have a function, you can train something to do that operation for you. So you can do it also on audio signal. You can add noise, background noise to the audio signal, things like you're changing the sampling rate, just do random shifts inside the audio. Or, for example, in the text, you can play with the syntax of the text, right? You can just change the dictation, like the wording, spelling, right? So just add mistakes to it, right? You can do shuffling, right? You can just use equivalent words, right? You can do all of those things. As I said, nowadays we do them less because the LLMs are doing all of that for us. But early days, people used to do the engineering, and it was a kind of useful thing, right? Now, this is what I told you. This is data augmentation. So what you did, you had your data. You got one of the data out of your data set. You did a transform on it. You got a new sample, which you do not have it inside your data set, but that data still has the same label, so you added it back to your data set, right? That is different from what we call a synthetic data generation. And you already have done synthetic data generation in assignment 1. Do you remember that? What you did? So you remember this example, right? That we wanted to just train the neural network for the dummy physics example, right? And there, what we did, when you wanted to make the data set, you just sampled H and V randomly. Yeah? You just made them positive because you wanted them to be positive. They're supposed to be positive, right? And then after that, you just computed the label D with this function because you knew that V, H, and D are related in this form, right? So you got your random V and H generated. You passed it through the process, this Newton law, and then you ended up with your label, right? This is synthetic data generation. This is different from augmentation, right? Because you did not use any sample inside your data set. You eventually had no data set, right? You made the data set, right? How you did it, you just started from a random seed, right? Each random seed gives you different V and H, and based on that random seed, you get your D, right? From the process, right? This is one sample. You change the seed, you get a new sample, and so on, right? So that is a different thing as compared to that one. So what you do here, you just know the process that the label, for example, is produced from the input. You also do know what are the properties of the inputs. In your simple case, are the properties that they should be non-negative, right? And then you just start from a random seed, you generate those inputs, and then you do the process, you get the output, right? Now, for our dummy example, it was too simple, but you can think, for instance, in physical environments. Sometimes you are able to do EM modulation, for example, right? So, EM simulation. Like, you want to really know what is the power level of the electromagnetic wave in this room if you have one particular antenna being located here, right? And then you can write it down out of electromagnetic Maxwell equations, and you know that, okay, in that point, the electric field and magnetic field are that, so you can compute the power and things like that, but this is a very exhausting job, right? So you have simulators which can do it for one, say, predefined environment. So you define this room there, small room, then the equation's going to get simple, and it's going to give you. But then you can just collect a few sample points, right? So you would say that point, this point, this point. I'm going to compute the power, right? And then out of those simulations, I have a few samples, and now I train a neural network which looks at the, for example, location of the antenna and give me a rough estimate of what is the power everywhere, right? So the function that you want to know is super complicated. You can just compute it at few sample points, and then out of that you want to just learn the whole process. So again, you can generate synthetic data, right? Because you can think of a randomly antenna being located here, random points, you compute them with your simulator, and that's it. This is, for instance, something that we use a lot in reinforcement learning. Actually, this is the way that deep learning got into reinforcement learning, because reinforcement learning by default does not really need any deep learning. I mean, the formulation is very clear. The only issue is that when you get into computing the value function, you cannot do it. Because it's very complicated. You can just compute it at few sample points, right? And then you use those sample points to learn the whole value function. This is, again, the way that you can do it there. So this is synthetic data generation. This is different from augmentation, as I said. So in augmentation, you look at the samples you have, CAD image inside your data, so you only transform it, right? So this is different from generation. You should just be careful about that. One thing is that you might say, okay, synthetic data generation simply makes sense when we are doing scientific environment, right? When we work with some scientific process. But, well, I mean, I guess this was a kind of argument people would give a couple of years ago, but nowadays, given all of the generative AI, you know that you can generate CAD images, right, from noise. So you just start from random seeds, you generate CAD images. This is still data generation, right? And then you generate that CAD image, you add it to your data set with label 0, right? You can do it. So this is why really we don't care about those classification problems too much anymore, right? We can get as much data as we want. Okay, so now if I want to just write it down a bit formally so that you get the feeling and we can somehow gradually introduce the idea of data distribution, well, I can call this particular A to be the transform that I am looking for. And this A, what it does, it's going to get a data sample X, and it's going to return one new sample, which is not inside the data set. Now, I told you the transform gets CAD image, gives me CAD image, right? But it doesn't really need to get one single CAD image, right? It can get multiple CAD images and give me still a CAD image, right? So you don't really need A to operate on a single sample, right? You can get A, and it operates on all the data set that you have, right? It's going to look at all the data set and generate you one new CAD image, right? It even does not need to really give you a CAD image, right? Maybe you give it 5 CAD images, and it can magically generate you one doc image, right? If it can do it, it's still okay, right? Because that dog image, as long as it does not belong to your data set, this is still a new sample. You can add it with the label 1, which is label of dog, right? So you don't really need to think about one transform which gets one sample and gives you exactly the same sample with the same label. It can get any sample from your data set, any bunch of samples from your data set, and gives you one sample. But what should be the key property of that sample? It should be cat or dog image, right? It should not be frog image, right? Because you are not working with the frogs here, right? So you care only about having valid label, right? You need to have a valid label. You don't want to have invalid label, right? So data set goes in, something comes out with valid label, right? And this is the way that we can formulate data augmentation. So we can call data augmentation A. The whole thing is this process A. So A is the algorithm, the technique which is doing data augmentation. It's going to look at your data set D, and it's going to return you a bunch of new samples. They have valid labels, right? They do not have invalid, because if they have invalid label, then they are useless, right? They're actually going to harm your training, right? So new samples coming out of it, and they are all coming from the same data set. They are generated based on the data set that you had, and they all have valid labels, right? The labels from the classes that you are considering in your problem, right? So this is data augmentation. If we want to just contrast it with synthetic data generation, this is different in synthetic data generation. You don't give any data set to your algorithm there, right? So you have this particular algorithm. This could be your generative model. It could be your simulator. It could be whatever you think of, right? And then you're going to start from a random seed, right? Something you generated randomly, random noise, anything, nothing from your data set. And through some process, it's going to generate you some samples. Again, those samples should be coming from valid, should carry valid label, right? So still, you want those images coming out of the simulator to be cat or dog. You don't want the horse or frog image, right? Everybody's clear, right? So this is the different idea of adding data or generating data. This is synthetic data generation. This is data augmentation. Now, if we look at the description that I have given, or definition I have given here, you see that I'm saying that both of them are operating on something. So augmentation on the data set, here on a random set. And then it's going to give you samples from data distribution. Samples from data distribution, I call it, right? And what does this data distribution mean here? The exact word data distribution. So here, when I talked about cat and dog, I told you I simply mean that I want valid label, right? I don't want a frog image, right? So this somehow comes from the fact that my data distribution is 0 for frog images. Well, I'm going to explain it shortly. But what I mean by data distribution, I simply mean that that image is a typical, a valid image coming for that data set, right? Now, why you said I don't want a frog image? Because you know your classification problem is cat and dog, right? And for this data, the probability of having some frog image is 0, right? You're not going to have 0, right? So this is not happening, and this is basically the idea of data distribution. Now, if we want to just make it clear, because this is, if you understand data distribution, this is going to be the beginning of what you do in generative AI or unsupervised learning. We're going to do it later in chapter 8 a bit, but just to give you a rough idea, because this is the way that you can get better sense about the whole learning process. So let's think about MNIST data set, right? And let's understand what does data distribution for MNIST data set mean, okay? So this is one handwritten image, right? And handwritten digit, 3, right? If you think about it again in form of pixels, then there are a bunch of numbers here in this pixel, right? So if it's MNIST image, what is the size? It's 28 by 28, right? So it means it has 784 pixels, right? Now, every single pixel in this image, what it can be? It can be 0, 1, 2, go on till 255, right? So 256 possible values. These are the values you can see here, and you have 784 of them, right? This is one image inside MNIST. Now, these are 8-bit images. This is what we call 8-bit image, because every pixel is shown by 8 bits, and this means that every single pixel could be either 0, 1 till 255, right? One of these numbers, nothing else. And the other thing is that, well, we know that this image is a handwritten digit, right? So we don't expect to see some cat image here, right? We just expect to see either 0, 1 till 9, right? One of these digits written by hand, right? This is what you expect. Now, one thing that you can for sure see here is that the MNIST data set, I mean, if you include both training and test data samples. If you collect all of them, in total it has 70,000 samples, right? Can you claim that these 70,000 samples are all possible 28 by 28 8-bit images? Can you claim that? No, and I'm going to show that for you. We are far behind that happening. And this is not including all of possible 28 by 28 images. This is one thing. The other thing is that it does not even contain all possible handwritten numbers, right? If you say no, it contains, I challenge you, I just take a paper and write one new handwritten digit. And I'm pretty sure mine is not there, because when they were collecting, I was not there, right? So it does not definitely include them, all of the possible cases, handwritten images as well, right? So this is a kind of representative of that kind of data, right? So let's just do a bit of calculation to get sense about that. So I have 28, I told you, 28 by 28 pixel. It means that I have in total 784 different pixels, right? And each of them is one of the 256 different cases, right? How many of that images we do have? Can you count it? If I have 1 pixel image, okay? Just 1 pixel. How many 8-bit 1 pixel image do I have? How many? 256, right? Because that one pixel could be 0, 1, 2, 256, right? 256, right? If I have 2 pixels, how many of them I do have? Square of it, right? Now I have 784 pixels. How many of them I have? This guy to power 784. That's fine. I mean, it's a big number. It's not infinity yet, right? Correct? So that is the number, 256 to power 784, right? It's a big number, right? If you just want to have more feeling about this, okay, 256 is 2 to power 8, right? So you can write it 2 to power 8. It's going to be then 2 to power 6,272. This is the number. And 2 to power 10, you can roughly say it's 1,000, right? 10 to power 3. So instead of 2 to power 10, you write 10 to power 3, and you do the math. This is the final number, right? So it's roughly this number, 10 to power 1,088 right? 881, right? This is the number. Is it a big number or not? Yeah, I mean, I guess this is more than all particles in this universe. It's more than anything that you can think of. It's not infinity, that's right, but it's still very large, right? Now, how many samples you have inside your MNIST data set? You have 70,000 of them, right? And this is by no means compared to that one, right? That one is even less than 10 to power 5, right? So you are far below the number of possible images, right? So obvious, my first point, you do not have all 28 by 28 8-bit pixel images, right? You don't have this. Now, one other thing is that obviously you don't have all of the handwritten digits, but not all of these images that I told you, this 10 to power roughly 2,000. So this 10 to power 2,000, not all of them are MNIST images, right? For example, this guy is again 28 by 28. This is 8-bit pixel image, but it's not handwritten digit, right? So this also counts here, but this is not inside MNIST, right? So you get the idea. I have this huge number of possible images, right? Some of them are inside MNIST, some of them are not there, right? But definitely, those which are in MNIST are still much larger than 70,000. You can guess, right? Even if you think a very tiny portion of them be inside MNIST, that number is huge, right? Clear? Good. So this is the moral of the story. So we have so many images. Not all of them are MNIST, but, well, a lot of them should be MNIST images. And we have only 70,000 of them, right? And this is the reason that we can think about something that we call a data space. So what is data space? Well, it's not here on the Earth for us, right? Maybe in the parallel world somewhere else. I mean, this is just mathematical definition. This is not the reality, right? So you can think of one set, right? And inside that set, you have all 28 by 28 images which look like handwritten digits, right? That set is huge. We don't have access to, but we can simply say that the samples that we see in MNIST data set are coming from that set, right? That is possible to define, right? So this is the idea of data space. So a space of possible data is eventually the set of all, in our case, labeled data points whose label is valid, right? So handwritten digit has label 0, 1 till 9, and then as long as you have 28 by 28 pixel, which can be labeled like that, then that is one possible data, right? And then the space, the set of all of them is the space of possible data, right? So in our example, it means that we have one of those images, one of those big numbers, 2 to the power 6,000 roughly, images that you have, those images which look like or can be classified as a handwritten image, they are all inside that set, right? And this is a very huge set, right? Now, what you can, this is just to indicate that this space is just a definition, right? You cannot say really I have it. Maybe for some dummy, very dummy example, you can build that set. But in practice, for the practical problems that you have, this set cannot be really specified, right? You cannot even count how many members are there. Yes? Yes, it should be correctly. But we are going to get rid of that as well. I mean, because this is not a very solid definition. But this is why we define actually data distribution, because this is still not good enough. As you say, like, how can maybe this digit or this image is classified, or some people consider it handwritten digits, some people not, right? So you cannot really talk about it. It's not a kind of binary logic, yes or no, right? It's a kind of fuzzy logic, because some images, yeah, it might be handwritten 3, right? Yeah, so you cannot really define it. This is why we go for data distribution. Okay, so now, yes, and that would be this. And what we have, the MNIST data set, as I told you, this is eventually the data set or a subset of that data space that we can think of. And what we can now say, we can say that those samples inside MNIST data set are somehow collected from that original data space, right? So it's like you can think of one machine, one genie who has access to that set and is just collecting a few samples, 70,000 of them, and put them inside this data set that you have access to, right? Now, but the question is that how do we collect those samples from that data space? Well, in practice, what we do, we go out there and we tell people just write down 3, write down 1, right? And this is just a random process, right? So what you can think that there is one guy who is just randomly picking this stuff, yeah? Or there's one random machine. Each time that you press the bottom of this is going to get one of those samples randomly and put it inside your data set, right? So this is the way that we think about the data set. We think the data set is a random collection of the samples inside that data space, right? And this is the way that we define the data distribution, because data distribution makes more sense as compared to data space, because it also gives us the frequency of something happening, right? If you ask some people write down 3, well, people can be very lazy and do very bad 3, right? But most people are going to write a fine 3 for you, right? Most of the samples that you get going to look roughly the same. There are a few samples which are not so typical, but they are still 3, right? Or they meant to be 3, right? So because of that, you have like a kind of frequency of pixels happening, right? So most 3 pixels going to look the same in many of, most 3 images going to look roughly the same in many pixels, right? Whereas some of them are not looking like that, right? So there is a bit of frequency, a bit of probability distribution for them somehow encoded inside the samples you're collecting. Now, the way that you can think of, as I told you, you can think of a machine which has a button, and then each time you press, it's just randomly picking one guy from that space and putting it here for you, right? And in the case of MNIST data set, you can think that we just pressed this button 70,000 times, right? And we got 70,000 samples inside our data set. Now, this is the way that we define the data distribution. And defining the data distribution makes life much, much easier for us as compared to just working with the data space or the space of possible data. So what is data distribution? It's basically the distribution by which you have sampled your data from the data space and put it inside your data set. Now, that is the idea. Now, what do we mean by that? Again, this is like the data space. It's just a mathematical definition. For many practical cases, you cannot find out what is that distribution because, well, it's very hard. It's a very high-dimensional distribution. You cannot really understand it. But one thing that, so you don't have really understanding of this because this is like data space. Like, it's a very abstract definition. But one thing that we can do with this definition is that we can think about probabilities. And these probabilities are going to help us a lot, right? For instance, this guy is an MNIST image, right? Correct? So it's a 28 by 28 image, so it belongs to that big set I told you, this 2 to the power 6,000 something, one of them. And then this is going to happen with some probability not 0, right? So this means that if you want to have one image inside your data set, this guy could be one of them, right? And this is definitely happening with something non-zero, right? But what about this guy? This is definitely not MNIST image, right? Correct? And this is happening with probability 0, right? So you don't really need anymore to look at that giant set of possible images and you just break it into half or 2 parts. One of them is possible data, one of them is not possible, right? You don't need that because just breaking it into 2 pieces is not a very concrete way, right? As I said, maybe there is one handwritten 3. Some people consider it handwritten 3. Some people say, no, it's not handwritten 3. It was something else, right? And then you can say, okay, this is going to happen with a very tiny probability in my data set, right? So it's going to make you like get rid of this issue with, classifying or harshly saying that this sample happens, this sample does not happen. But that probability P, well, you don't know it, right? Everybody's clear? Questions? Yeah.
Since the model's flaws should at least mimic the distribution,
Or data set should mimic the distribution, right?
So is it helpful to add replicator?
This is the whole process you do when you do data pre-processing. So you want to somehow make sure that your data samples that you have are somehow a good representative of that distribution. But the issue is that you don't have that distribution, right?
I mean, should we have replicated data?
When you replicate data, I'm going to talk about it, but if you duplicate it, as you mentioned, it could be it could be harming, right? Because you're going to just change the distribution. So you need to make sure that that particular duplication, whatever you are doing, you don't do duplication, but that particular transform like you do for augmentation, that is not changing the data distribution.
Well, according to for the high frequency samples,
Right?
it should suppose that like more data.
Well, yes, you're gonna have this. As I say, we are not talking. We are not saying that we want everything to be uniform. That's not the case. You're gonna have that distribution, like different distribution or different probabilities for every sample. Definitely, this is the whole purpose of defining the distribution. The key point here is that, I mean, say one thing is happening with probability 0.1. One other thing also happening with probability 0.1. And if you go doing augmentation and you add like transform of this and you increase this label, right? Say, for example, your data set has half cat, half dog, right? And if you do augmentation and you just add cat, right? Then you are just increasing the label probability for cat, right? Which is making your data distribution somehow change, right? So you should make sure that this is not really happening. But if you can say that, well, the original data distribution has more cat images than dogs, right? Then that's another story, right? Then you would say, I need to make my data set to somehow keep the same ratio, right? No. Yeah. Sorry? We learn it. I mean, this is the whole generative AI. Yeah, the whole generative AI that you consider this P to be some neural network, P theta, right? And then you want to learn how, this P theta, what is the right theta, such that P theta is somehow getting very close to the original distribution. And then you learn it, and there are different ways to do it. You can do it directly using maximum likelihood. This is what we do in autoregressive modeling or flow-based, energy-based models. And more sophisticated ways are indirect ways like GAN and autoencoders and diffusion models, the most recent ones, right? But all of them, what they do, they basically try to learn this guy. At least they learn how to sample from it, right? And yeah, this is the whole generative AI thing. We're going to have it in chapter 8 a bit. Okay. Questions? So you got the idea of data distribution, right? And now the data samples that you have, they are always coming from that data distribution. Now, if you just go and randomly open one paper in this area, okay? Most of the time you see something like this. So I just cut it from some paper. I don't know. I just took it a couple of years ago, so don't know really what was the paper, but it says that the learner has access to a small reference data set. I mean, the training data set that you have. ST, and this guy has these ones, of empty samples drawn IID from a target distribution DT. Basically, that target distribution DT is your data distribution, right? And then it thinks that all of the samples that it has inside the data set is coming IID from that distribution. This is the way that we do it as well here, right? This is the reason that empirical risk minimization is working. Because you assume these guys are coming IID, you put it inside the loss, you cannot compute the expectation, but you average it over those samples, right? And then you expect that this guy, by a law of large number, somehow gets into the true risk, right? All of these things are happening because of this assumption, and we cannot confirm it, but, well, evidences say that it's something working, right? Everybody's clear? Questions? Okay, so if you got no question, just one quick note. So we cannot, in general, have access to the exact data distribution, but we can try to approximate it. Early days, people just do it for low-dimensional data, like you have one height, right? Your data is the data set of height of people, and then you can, of course, draw the histogram and find out what is the data distribution. Nowadays, we do it by generative AI. So we put one neural network, we look at the samples, we try to learn the distribution. We can do it. It's like a very advanced topic in deep learning, but this is what the state of the art is right now, okay? So now, just a few notes now on some practical terminologies that you might hear in practice and why they're like issue in practice. So one of things is about the data cleaning approaches. So there are different approaches inside data science, and then people try to just think exactly the way that we did here. So they assume that the data they have is coming basically from a data distribution. And what they try to do, they try to find out a way that makes sure that this data set that they have is a kind of good representative of that data distribution, right? So as I gave one example a bit ago, so if you have a data where, you know, the labels are happening uniformly, right? So you need to have your data set also containing the same amount of samples from each label, right? So if you have cat or dog image, and you know that because the number of cats and dogs in the universe are roughly the same, for example, then the labels should be 50-50, right? And then you see that your data set has 80 samples, 80% cat, 20% dog, then this is not a good representative of your true data distribution, right? So one thing that you want to make sure is that your data set is a good representative of the data space and, of course, data distribution. And if it is not, how you can handle, how you can do something to make it a better representative. And this is the whole idea of data cleaning. So by data cleaning, I do not mean that you get the image and convert it into tensor. That is not data. I mean, that is also preparation of data, but this is not what I mean by data cleaning here, right? So you have your tensor already in hand, right? You just want to play with the samples to just make sure they are a good representative. And there are courses like on data science, right? And those courses are basically working on these approaches, right? So there are statistical methods to just confirm this, right? And I'm not going to teach any of them because this is not a course on data science. But if you are interested, they are very interesting topics. You can go ahead and just study them. But we are going to talk about a few terminologies here. For instance, duplicates, right? There are statistical ways that you just go ahead and find out the duplicates inside your data set. This means by duplicate, we mean that one sample is exactly repeated out of mistake, copied once again inside your data set, right? And if you do that, if you leave it inside your data set, you are harming your training because you are making your data set not representing the right data distribution. For instance, say I have B different samples, so these are just collected from one data distribution, and if I want to train it without any duplication, I'm going to do this averaging, right? This averaging is estimating the target expectation on the data distribution, right? So instead of taking the expectation of the loss, which was the true risk, I am averaging over the samples I have. If those samples are really representing the data set, then this average is roughly a good estimator of that expectation, right? But what's going to happen if I have m duplicates of one particular sample? So say I have x1, v1, and by mistake I just copied m more times inside my data set, right? So what's going to happen? Well, the first b terms are the same, right? So you start from x1, v1, x2, v2 till the last one, right? They are the same in your loss. They are still there, right? But you have m extra copies here, right? So you can write m times the loss of the first guy, right? That's correct, right? And now this is the whole summation. Now what should you do? How do you average it? What would be the number that you should divide it by? What is the total samples you have? B plus m, right? So you're going to just divide it by b plus m, right? And if this m is a large number, now you're changing the data distribution. You are not averaging over the data distribution, right? You're averaging over a bias distribution, right? And this is or bias estimator of your distribution, which is not a good thing, right? So this is why people are not happy with duplicates. And there are ways that you can, for example, find out if something is duplicate or not, right? So there are more advanced statistical approaches. I just want to give you one dummy example that you see there are ways that you can find out if something is duplicate or not. For example, say you go out inside the campus and you ask people about age, education, and place of birth, And as the label, you also ask them how many child they have. Okay? This is a questionnaire you are filling out. This is your data, right? The X is, the input is age, education, and place of birth, right? The label is the number of children they have, right? Now, if you go out, you can find lots of people who are 22, they're doing their bachelor, or they just finished their bachelor, and they were born in Toronto, right? And they are young, they are not married, they have no child, right? This is possible, right? This could happen, right? And this is not just one guy. Probably you're going to see lots of them, right? So if you see lots of these people inside your data set, obviously this is not a duplicate, right? This is just indicating that the probability of this particular sample is high because you're collecting your data inside the campus of UofT, right? And if your data is just focusing on people at UofT, they are a good portion of people at UofT, right? So they should have high probability, right? This is different from this case where you just go randomly in the street and you ask people, what is your age, what is your height, and then you ask, this is the input, and as the label you ask them their weight, right? If you do that and some guy comes out, they say, I'm 48, I am this tall, 176.42, and my weight is 73.31 kilogram. If this happens and you see two of them inside your data set, well, this is fishy, right? How likely is that you meet two people randomly with exactly the same age, exactly same height up to 2 decimals, and exactly the same weight up to 2 decimals, right? This is very unlikely, right? And then you would say this is probably a duplicate, right? And you're going to remove it, right? You agree, right? Everybody's clear? Now, yeah, go ahead.
I was going to ask, how do you tell in the other one if there's duplicates or not?
Yeah, I didn't say that this is a duplicate or not.
If there was actually, if there is a duplicate,
Right.
given that it's statistically likely to have
Right.
independent samples,
Then you cannot find it, right? So this is why I told you there are statistical methods, right? So this is basically what I wanted to mention right now. So you are talking about likelihood of things, right? And you can always compute some sort of likelihood out of the samples you are collecting, right? And you always have also some prior beliefs which help you to just form that likelihood, right? And all of it going to come handy when you want to do a statistical approaches, right? So at the end of the day, by statistical methods, you cannot say for sure this is duplicate, this is not duplicate. You cannot say it, but you would usually say that, okay, most likely this is duplicate, most likely this is not duplicate. Or removing this one going to harm, removing this one probably is not going to harm that much, right? And based on that, you usually put a threshold. You would say, okay, I want the likelihood or whatever p-test, t-test, whatever I do, the number I want to be below 0.1. And then as long as this is below the threshold, I'm going to take it, right? Yeah. This is, as I said, like more advanced. You need to know all of those statistical tests. But I just wanted to give you a rough idea how they work, right? Intuitively, at least. Everybody's clear? Questions? Yep.
And just for the previous slide, so when you have, so for the previous slide,
Right.
when you have duplicates, then,
Right.
then the average came out to be, oh, it's B plus M on the bottom, right?
Right, right.
But this seems to have maybe a lower loss value than the previous one.
Yeah, but it's, the issue is that at the end, what you do, you try to train your model with respect to the neural network, which is somehow hidden inside Y, right?
Yes.
And when you try to minimize this one, the model that you get is not the same thing as the model that you train to minimize the first guy, right? Yeah, this is the key point, right? It's true that you can make the loss smaller. That's right? First of all, it's not necessarily the case. If your particular sample has very high loss, right, then this is getting more pronounced in this averaging, right? So you cannot say it for sure, but even if that happens, still you are just minimizing the wrong loss, right? And at the end of the day, by training, you're going to make the loss, say, roughly 0 for both of the cases, right? But in the first one, you somehow got inclined to just pay attention more into the particular label or sample, which was too much replicated.
Just different than that.
Yes, yeah, exactly. So this latter one is not the right estimator of your risk, right? It's a bias estimator. And so you are going to somehow get bias at the end, right? This is why, like, still, I mean, most data sets that we have in practice have this problem, right? So if you, for example, talking about the images of people, right? So most data sets that we have collected have been built in specific part of the world, right? Many people from other parts of the world are not included in that. And then when we use that to just train some model to generate image, we see that people coming out of it are, again, from those communities, right? They are not inclusive, they are not diverse, right? And there is a huge literature on this issue, how we can somehow diversify all of these data sets. I mean, there is a huge threat to, you know, AI goes towards, again, discrimination and other stuff, which is a topic really in human science. So, yeah, that was about duplication. One other thing that we could have is the outlier. So what is outlier? Outlier is basically the data sample, which is quite abnormal as compared to the other samples that you have, right? So one example that you might think always is this guy, right? So you have everybody exactly lying on a line, but there is one particular sample which is totally away from that line, right? And if you have this guy, if you don't have this one, and you want to train, then you're going to end up with this line which say this is the true function, right? Whereas if you just train it on the whole data set, then you're going to get a line which is far away from the true function, right? Now, again, this guy is hard to say, right? Because you don't know whether this is really coming from the data distribution with high probability, and this is simply abnormal because you have few samples, or it's simply coming to happen to be one particular non-typical sample, right? So if you are thinking, again, in terms of data distribution, each time you press the button, you're going to get a kind of typical output coming, right? But it could happen that one particular sample is just happening which is not typical, right? And if that happens, probably that thing is not going to happen for a long time again, right? But what if you were unlucky and when you were sampling, you just got that particular abnormal sample, right? And in that case, then this is a kind of outlier. This is what we call it, outlier. And if this is really something that is not happening inside our data set that much, as long as we include it inside, it's not happening with the data distribution that high frequency, then as long as we include it inside our data set, we are going to just make the whole training harmed, right? Because your training is somehow considering this particular outlier, which is not supposed to happen, considering it a kind of serious sample, right? And then tries to also get the pattern out of it. So finding outlier, again, you need to know some statistical methods, right? So you look at the data that you have, you just compare one sample against the others, and out of that, you start to get some sensing whether this guy is an outlier or not. Again, you talk about everything in terms of probability. You cannot say it for sure, right? And there are, in general, two different types of outliers. Bunch of them are called univariate outliers. It means that you look at your whole data. It could be multidimensional, just including lots of different parameters in it. But just looking at one of them, you can say whether this guy is outlier or not, right? And if you want to just have an example, say you have the data points, and these data points include lots of information about every single individual. So it's weight, height, I don't know, age, education, birth date, many things, right? But if you just look at one particular entry inside this data sample, maybe you find out that that data sample is outlier. For example, I have given this this example, Sultan Kuzin, I guess. He's, I mean, at least up to last 2 years ago, he was the tallest alive person on Earth. Okay, and his height is 2.51 meter. Okay, and now you look at this data sample, which has all of them, right? But then you just focus on the height, right? You don't look at the age and anything else. 2.51 is not typical, right? So when you look at everybody else's height, you see somewhere between, in one range with average 170, 180, right? And then you see that there is this particular guy who is 251, right? So he's obviously an outlier, right? So you really don't need to check his age or his weight, nothing, right? Only the height is telling you that this is outlier, right? So this is a particular sample, right? And now, if you're talking about a typical sample of people, then this particular guy is not inside that, right? Because this is happening 1 in a billions of people, right? But what if you are unlucky? You're collecting data exactly where he is living, right? And this is coming inside your data set, right? If that happens, then your data set is also including him, right? And by including him, you are giving high weight, because at the end, you have 100 samples, right? So you would say height 2.51 is happening with a chance 0.01, right? Whereas in practice, it's not happening with that, right? 1 in billion, right? So this is obviously an outlier inside your data set. There is also what we call it multivariate outlier, and this means that maybe every single entry inside your sample is fine, right? But when you see them together, they are not matching, right? And this guy is harder to be detected as compared to the other one, right? Because then you need to know the joint distribution of the entries. Same example I told you, height and weight and a bunch of other things. Now, say that you get this data, that the height for one sample is 182, which is a typical height, right? Many people could have 182, right? The weight is 24, which is, again, a typical weight for 6, 7-year-old kid, right? But if both of them happen for one sample, this is not typical, right? This is an outlier. Maybe that person is suffering from one specific condition, right? So this is, again, not typical, but you cannot find it out by just checking the weight or height. You need to just check them together to find out, right? And this is a multivariate outlier. You can think that in general you have, so many dimensions inside your data, and if you want to talk about multivariate outlier, you need to talk about their joint distribution, which is making it harder to get detected, right? So again, in practice, you're going to do lots of tests that to find out what are the outliers, and at the end of the day, you cannot say for sure this is an outlier or not. This is only you rely on the statistical results, right? Now, if you have one outlier, what you can do, if you're sure this sample is outlier, well, one thing that you can do, you can remove it, right? This is especially good if you have a simple model, because the simple model has low capacity, and it cannot grasp both normal data and outliers, so you prefer the outlier to be out, and you just work with the typical data. But there are also techniques that you can use in order to just get rid of that. Do not throw it away, because it's still a sample, but somehow lower its impact, right? For instance, if you are adding it up in your loss, you can just add it up with a significantly small weight, right? Because you would say in practice this outlier is happening with very small probability, right? It's happening at least at the end, but it's happening lower rate, right? So I just reduce the probability. I just reduce its share in the loss. There are also other approaches. You can take a look at a couple of names, Minkowski error and other things. These are, again, data science stuff. But if you are interested, or if you get in touch with them in your own project, okay? Questions? No questions.